Hi there, knife people here, lady and gentlemen. Today I am working on a double feature that includes both items that came to me in a Luminary set from Microtech. In case you don't know, it's a set of a knife and a flashlight from Surefire. So Microtech Luminary is a brand new design that uses zero tolerance, or what I call zero play lock, similar to deadlock on other brands, which provides zero play on the blade. And a flashlight is Surefire's newest and greatest, supposedly, flat form, dual output, pocketable LED light. The reason I'm not holding these items in my hands is right here. They're on my bench. Let me show you. The reason they're disassembled is because I conducted a series of torture tests on the knife and the IP rating test on the light. I don't want to spoil anything, so I'm going to move that out of the view. You'd have to watch that video, which will be linked at the end, to see how that went. For now, we're just focusing on the knife. So what have I done to the knife? The mildest thing was examining its edge under the microscope. Then I also tested its hardness, as evidenced by these divots here on the tang of the blade. I also took it outside and stabbed a few things with it. Also batoned it and tried to unlock the mechanism. And I also took it to the local body of water and tested its operation while submerged. So let's go. Oh, what a beautiful day to play with a knife. As you know, the blade has these two extended tabs on the back. See them peek out? And I wonder if that will help expel the water after the knife fills up. Extending and retracting the blade submerged informs me on how well the mechanism is designed to deal with whatever can get inside this knife. And after 3 successful deployments, the blade is not retracting on the 3rd try. We'll drain the water out here, try it again. I'm holding the camera in my left hand, so I'm forced to do everything one-handed. And I just can't get the blade to budge. It's locked in a forward position and is not retracting. Trying to see if I can push it against my shoe toe and push it back. It's locked open pretty good though. Maybe this will do the trick. Aha, it sure did. As I always say, all automatic weapons jam once in a while. It's how quickly you can clear the jam without the use of special tools, just using your hand. It's the reflection on how good the design is. Meanwhile, it's jammed in the forward or blade deployed position, and trying to do the same again, and trying different angles of operation. That unlocked it. Later, I discovered that pulling back on the switch and then releasing it rapidly unlocks the blade, and then to get it back into battery, rather than doing these cavalry style slashes that you see me do here, it's better to just give it a quick vertical joust, and then it will go into battery, either open or closed. Let's try to think out loud and decide what's causing it to, I wouldn't even say fail, but if it does fail to unlock, I don't think it's a critical detriment to the functional of the knife. It's not a critical mission failure, because the mission of this knife is to serve as a last line of defense, and that makes deploying and locking in a deployed position a lot more critical than retracting, because if it's deployed, you can continue, fulfilling the mission of this knife until you no longer need it for whatever reason. And then there's a little bit of that struggle closing it up, but you could leave the scene with a knife open if you had to. Anyway, so while it's a failure, I wouldn't call it critical. And by the way, this I just quoted you a definition of operational mission failure as our military equipment testers use it. So this is where the magic happens. This is the interface between the blade and the frame, and it has a taper, and then the bevel of this channel is probably matched to the taper almost exactly, or as exactly as possible. And when the knife gets fully deployed, that drives the, I call it UFO because it kind of looks like a flying saucer. It drives it into that angled channel here, angled section of the channel, and there it rests its taper against the bevel of the channel. So I think what happens here, so the engine is engaged to the UFO, the captain's bridge on the UFO, and when I pull on a switch, which is engaged to this little tab there, right here, when I pull back on it, it builds up potential energy in the springs. And once the force in the springs reaches a certain critical point, there's enough of it to disengage these locking gates and start moving the blade backwards. If you know more about this type of mechanism, feel free to write as long of a comment as possible. I read them all, and the more technical, the better. Let's check out the next demonstration. I believe what sets a great OTF apart from a not so great OTF is its ability to resist forces induced by forward thrust. In other words, no matter what you stab and how hard, the blade should not unlock. And that's why I'm doing what you see here. And the goal is not to break off the blade, but rather test its ability to remain locked under lots of stress. And this particular knife takes longitudinal stresses pretty well, which is not always the case. During my recent demonstration of the same with a Bear Ops small OTF, it unlocked on these lateral strikes. And this knife didn't, so I'm continuing. Now I'm inducing a torsional stress on the mechanism to see if it will unlock. And it's like a vault. It's like a fortress. It is not unlocking at all. Trying again. Nothing. Those locking tabs, I call them locking gates, they stay engaged no matter what I'm trying to do to it. Rather than just telling you, I would like to show you what I mean. Those tabs, or specifically this tab, engages this locking gate right there. That's what I call locking gate. So if I put the knife blade, if I put the blade back in like so, it bottoms out on the gate. If I get the gate out of the way, let me get my big finger out of the way. There you go. Now the knife can go and retract, and then it will lock again here onto this gate in a retracted position. So that's what I'm talking about when I mention locking tabs, locking bars, or locking gates. Back to the hype stumper. That's what I call this tree stump now. For a bit of drop testing. Here I hold the knife by the blade at the shoulder height and drop it on its pommel, and that causes the blade to unlock. Sorry about the camera angle here. Anyway, this shaking motion up and down locks the blade into close position. And now I'm going with the blade down drop, and it holds. One more time. And let me reiterate, I think this is the mission critical mode of operation. Let's try a little bit more stress. I am so looking forward to the comments how I am not supposed to use an OTF this way, but it's my knife now, and I choose to do this for your entertainment. Not that I recommend you do it at home. Before we get under the microscope, let's talk about what you are actually paying for in this very expensive knife. So my estimate when the production version comes out, I estimate the price will be between $800 and $1,000. And here's the reason why. After this blade gets heat treated, it needs to be set up for final grinds. But before it gets heat treated, it needs to have this hole drilled and channeled, not to mention all this milling done to accommodate our interface with a flying saucer. Previously, I speculated that this pin that engages crenulations on the flying saucer is spring-loaded. Actually, I was wrong, and I will show you under the microscope. Here's the pin, and I'm going to use the screwdriver to try and depress it. And it's clearly just screwed in and not spring-loaded. Single part. And here are the quarter spherical crenulations in the flying saucer's edge there, and the pin engages them. So while you're torquing the flying saucer in, you can hear a little bit of a ratcheting. And then when you reach the tight engagement, you screw in the pin and it locks into one of these crenulations. I've seen something similar on older firearms, turn of the 20th century or so, but I have never seen it on a knife until now. If you have seen it, let me know which knife was it on. All right, let's look at the blade starting with the tip. It's a really well formed tip. All the lines come to a point as they should. This symmetricity of lines is a must have, not just for cosmetic purposes, but to provide a stronger tip. Flipping it over now, let's see. Looks great, even under this 40x magnification. And here are the two grinds. I'm trying to turn it so you can see the striations. So it looks like all of the grinds were machine made. Maybe not. So right here you see a little bit of a convexity. So potentially somebody ground it on a belt sander by hand. And that's why you see slight variations in the width of the grind side to side. That usually is another piece of evidence supporting the manual grind theory of mine. Because people have a dominant and a non-dominant hand, and that reflects in how wide the manual grinds end up being. Nothing you can't fix at the first sharpening, but the sharpening is challenging because you really have four sides to sharpen. And because of the angles of the primary bevels, it's not trivial to clamp it into a fixed angle sharpener. I might have a video about that soon. Please don't forget to subscribe for that. The flip side of machine grinding is tolerance stuck up. As you can see, the flats that surround the channel are not perfectly centered as related to the channel. The one on the left is a little wider than the one on the right, actually visibly wider, even with a naked eye. On this side, it's a little better, but the difference still exists. That tells me that their setup feature on the CNC grinder is within some kind of tolerance zone and it's slightly off to one side. It is worth pointing out, however, that that flat grind is perfectly centered to the primary bevels. I think it's the channel itself when it was formed, probably press formed in the raw metal, was not exactly spot on. And here's a laser etching, says Luminary. On M390 MK, which is a very corrosion resistant steel, it's okay. And the burns are not very deep. So I don't think it'll pose a huge corrosion risk, but there will be some risk in this area nevertheless. And here I'm going to show you those little indentations. That's from my Lieb type tester. I had to strike it 5 times to get an average, which is what I'm about to show you. My Lieb tester is calibrated with a hair splitting accuracy using this test block which is at 787 HLD or Hardness Lib D scale. And I will prove it to you before I even start testing the blade. I will be running the stopwatch through the entire duration of calibration verification and the hardness test itself, so that you know I haven't edited anything in or out of this segment. Again, 787 HLD points as our target, and 1 point HLD roughly equals 0.2 points of HRC. I am satisfied with 788. There's almost no variance from the calibration. And now I'm going to use this sanitizing gel. It's an incompressible liquid that takes up any cavities that may exist between the tang of the blade and the surface of the block. And that's what allows me to test thinner metals on the LEAP tester. I validated this method through numerous tests. I have numerous videos of those tests that you can view on my channel. And I feel 100% confident this is an accurate test. I will even go as far as say it's more accurate than a traditional Rockwell test done on an inexpensive, under $10,000 Rockwell tester machine. Had to make sure the units are in HRC. 60.3 was the first one, and I'm looking for the average between the 5 strikes. I also weed out any outliers, meaning anything that looks too low or too high. And by looks, I mean within 3 standard deviations. My first average is 59.8 points HRC, which is spot on mid-range, safe range for M390 steel. M390 MK is a little bit of an enigma because Marfiones did not disclose the exact regime for heat treating that steel, although Dr. Laren Thomas has a video where he actually evaluates it to be right in the same ballpark as a regular M390. So we'll just call it mid-range heat treat, judging from the first side. But let's not jump to the conclusions. Let's reset the tester and test it on the opposite side of the blade. And the reason I test both sides is because flatness can vary by microscopic amount, which causes variations in the tested results. Here you can clearly see why the industry doesn't use this test method. It's a little bit tedious in the setup. It's a little bit harder to find a good spot to test as compared to Rockwell tester. And it results into a much slower process, which they prefer not to implement. You know, testing 5 to 20 blades in a row would take some time using this method. And here I realize that I don't have a good engagement between the blade and the test block, so I'm resetting the tester and I'm going to start it over on the same side. So I'm going to place the blade so that the wider part of the tang is on the test block, and hopefully this time it will go a little smoother. I feel like I drink way too much coffee, and that results into jerkiness to my motions. This gives you time to hit the like button or share the link to this video with your social network. I also would like to thank several of my subscribers who keep donating to the channel via the super thanks. That's another button there right next to the share and like. And, you know, I just want you to know that this is appreciated, and it's very humbling to get those generous gifts from you guys. Because of those variations that I observe, now that I have some experience with this tester, instead of calling out the exact averages, I go with a range. This average is 60.2, but I can say with quite some confidence that this blade is treated to 59 through 61 HRC. Inertia is a major factor in how OTFs deploy, and in this short segment, that's what I'm trying to demonstrate. Namely, that the angle and the speed of motion with which I deploy the blade does not cause it to stay unlocked. And it is only while I'm doing the retraction the blade stays out of battery. And here, in my opinion, is the best way to re-engage the blade in this zero plate design. Again, I don't consider it a mission critical failure because it can only happen after the knife did the job. That said, always make sure that the blade is in a retracted battery position before putting it in your pocket. You can probably deduce that I'm extremely satisfied with the performance of this knife. However, if you're considering even remotely purchasing the anniversary set that includes the Surefire Stiletto Pro II, please watch the companion video and don't be hasty in pulling the trigger. The video is coming up right now.